Alrighty. Hello, everyone. Welcome to the June CentOS Automotive SIG meeting. We are going to dive straight in because we have a very special guest today and just a couple of tiny announcements beforehand. So, the one of the nice, exciting things I wanted to announce is some documentation on Herta. Herta, of course, is our lightweight container orchestration system. There is now a significant amount of documentation at herta.readthedocs.io. It is automatically generated and it looks gorgeous. So, and it has some getting started information out there. So please go have a look. The other thing I wanted to mention is that on June 16th this year, in what, 2 weeks, week and a half, devconf.cz will be happening in Brno in the Czech Republic. There are a number of automotive talks. I believe they will all be recorded. I'm not totally certain about that. But if you happen to be in the region and want to go, it would be an excellent place to go learn about automotive stuff and containers in cars, particularly here at Dell. So with that, I am going to hand it over to Philip, who is from IoT.bzh. I'll let him introduce himself. I will stop presenting.
Okay, a tab, a window, your entire screen. So a window, I suppose. Okay.
Window tends to be the easiest. There you go. Yep, I can see it.
You can see it?
Yep.
Okay, I'm going to talk today on how we do the maintenance of board support package, and especially the one we are pulling out of Yocto, and how we maintain different embedded boards based on the CentOS Red Hat source code, and especially in RPM using Koji. So on this picture, you don't see an automotive engine. This is a boat engine. Okay, it's a 100-meter long boat. In fact, it's a tuna fishing boat. So we have a little more space than we typically have in a car. Okay, it's a little bigger. Quick word about us. We're located in Brittany, South Brittany, on harbor city named Lorient, which is very famous for racing boats. We are 30 engineers specialized in the embedded world and on Linux. As you can see, most of our partners are from the automotive sector, but we also work in the energy and aeronautic, as well as navigation and commercial ship mostly today. So in order to start on how we are looking and working on the migrating in between CentOS and Yocto and use RPM or layers and how we maintain all of that, it's important to come back on few facts. So if we look for CentOS Automotive, today it is based on CentOS Stream 9, which is a rolling distribution. Linux kernel is 5.14. We have regular update with CBA fixes, and you support two architectures today, Intel and ARM. If we look for the production side, at least at IoT.bzh, we derive from directly from RHEL 9. So it's more or less the same thing, except that we have obviously a different roadmap and we have more stability. But at the end of the day, from a coding point of view, it is exactly the same thing. If we look on the BSP side, and I took a Renesas R car as a sample. Okay, I could have taken a different one, but this is a very popular board within the automotive sector. So today they have a BSP that is on the 5.1.4, aligned with Yocto Kirkstone. There is a plan, obviously, to move to next release, and current version is going to be end of life roughly in 1 year from now. Linux kernel is 5.10. Okay, so we see the shift is not that big, in fact, in between what we have in CentOS and what we have in the embedded board. Obviously, depending on the board, we have different version of kernel. But I would say, at least for recent board, we rarely have a huge shift. Now, if we look for what has been modified, okay, and what is going to create us trouble when we want to move to the RPM world. We have few things, okay. The first one is the ones that are the original recipes that we have in Yocto, so mostly in BB file, for some specific component of the hardware. Obviously, we have the Linux kernel, which is, as I said before, a specific version, which is typically aligned on Yocto. But we also have some core tools, and especially we have the ARM trusted firmware, we have the U-boot, we have Opti, and we have a few other things like UDEV, rules, STRAS, and so on that are, I won't say 100 specific to a hardware, but that are typically modified to support some specific feature of the hardware. And also some very specific component to the embedded world, like ICCOM, for example, that is used to negotiate or to exchange data with ICCOM socket. Most of the graphic is also specific, especially the acceleration, which is going to impact library like LeadGBD, EGL, GLS, and so on. So here again, it's not that we have 100% specific code, but we have some specific plugins that we have to recompile for those libraries. And multimedia at large is a nightmare, okay? Because in multimedia, you have a lot of specific codecs, you have a lot of proprietary stuff. You sometimes have some specific, accelerator as well. And very often they are not open source. Okay, so it's a kind of mix where you have a binary blob that is proprietary, and you have to understand how you're going to align that with your open source stuff. So, but at the end of the day, I would say this part is relatively clean, okay, because everything is in a BB file, and you only touch really what is specific to the BSP. So, what is necessary to run your hardware. You have most different steps that are kind of not really part of the BSP, but are influenced by the BSP. And this is everything that is in between the kernel and the user space world. So things like systemd might be one, but also sometimes ncurses, QEMU, GCC, where you may have some specific option for your compiler. And obviously connectivity, and we already talked about the graphic and the multimedia. So in this case, we have patched a little everywhere in different BB app and file, and those one are really the hardest one to check for. If we look how we build that, so we're using Koji and all the like the Red Hat suite that we have integrated within a single factory to hide the complexity from users. But I would say we have main input on the left. So as we said, we have the Yocto BSP that we use as input. But we also sometimes have native BSP when we're lucky. Okay, so in this case, we don't have a Yocto, but we have a native BSP, or we have an Android BSP. And typically, we have a lot of upstream softwares that we have to download. So GCC, glibc, MySQL, and so on. All the different packages that make Linux so rich. I would say most of the company have some specific middleware that you also have to compile, and you have to tune for, especially the security model for your given hardware. And at the end of the day, you have the user application. And so you want to shake all of that, and you want to maintain that automatically for 10 or 15 years, okay? Because typically this is what the customer are asking for. So if we look for the migration path, in order how we move from Yocto layers to a factory based on Koji, I would say at least on Renesas, Renesas is a very good Linux citizenship. Okay, so typically their code is pretty clean. So the good point is that we see the kernel version are not fully aligned, but they're very close. Okay. And I just wrote, it's not true for all vendors, okay, because we also have some boards that are still running version 3 of Linux, and so it's a little tougher to move to a modern kernel. But we have some bad points. And I would say the hardest for us is that some base OS component have been modified by the vendors, okay? And Yocto is very cool for that, okay? Because in Yocto, you can change anything at any time from anywhere, more or less, okay? So then you have to track down who made the modification, where it was done, when it applied. And I just take one example. Typically, if you need to have a specific UDEV rules to support a specific device, the clean way is to create an extra configuration that is specific to that device without touching to UDEV dev3. But this is rarely how people are doing it, okay? Most of the time, what they're going to do is they're going to add directly in the UDEV config file from a BBapp layer, which is making your life a little harder when you have to transfer stuff from one world to another one, okay? And this model obviously is highly discouraged when you work with a standard distribution like CentOS. And I would say also more and more customers are, forbidden us from doing so. Okay, they want to have a clean separation in between what is standard and coming from the main line and what is specific to a given board. And as I already said, we have some integration, especially graphic, multimedia, and trusted modules that most of the time raise some specific issues because you have proprietary blobs, and so you have to deal on how you're going to deliver this and how you're going to maintain, these binary blobs that typically never change with everything else that is changing, not every day, but very often. Okay. Um, so when you start looking on how you're going to move to RPM from Yocto, uh, the first thing you have to check out is your kernel config, your kernel path, your bootloader firmware, and your bootloader patch. Okay, and you have to do a clear separation in between what is coming from the upstream world and what is specific to a given board, and have a clear way to handle what is official and what is your custom patch. And then you have to create a specific spec file for that. So what we've done at IoT is we started from the spec file of Fedora kernel, okay, that we simplified, okay, so we've done some cleanup in there. And especially we moved everything that the user has to change into macro in such a way that when you open your template, you only have few lines where you need to edit and change things. Okay, so we see on the left hand we have the empty template, and on the right hand we have what we have to fill in the template. So typically we have to obviously place the version, put the URL where we download the kernel from. And so it's very limited what you have to do, in fact, to move from the template to the spec file. So even if you're not a spec file expert, normally it's relatively easy to do that. We could have, obviously, in the ideal world, like a graphic interface to do that, but we do not. Okay, we just have a templating and we fulfill the template. And then obviously you have to enter your configuration. So nothing new on that side. Okay, it's a config file from kernel. And we see here the different element we have for a kernel. So the service.json is a file that allows you to download everything you're going to need to build your kernel, because as I said, we have to do that today, but we should also be able to do it in 10 years from now. So you have to make sure that you have everything in hand to rebuild your kernel. Then you have typically your kernel spec. That's your spec file, and you have a few configurations specific to your kernel, but I won't say it is short, because if we look for a real example later, we'll see that we have few things in, but it's not too complex. At the end of the day, the kernel is not a big part, in fact, in the BSP, at least when you have all the driver to support your hardware. And when this is done, then what we do is the kernel is only one specific application from a project, and the project is a BSP, okay? And so when we look for the different application in between double quotes that we have in a BSP, obviously you have the kernel, you have the BSP repo that's specific to our organization. This is where this is where you go to download extra module for your board when you do update and so on. So this is it could be included somewhere else, but we implemented as a standard application. And you have obviously the trusted firmware for most of the board. You have the configuration that is specific to your board. So in this case, the sample is a solid run board. So this is a NXP component. You have extra firmware that you have to upload to your board, and you have U-boot. Okay, and U-boot typically is something you have to modify because you need to implement first the signature to verify that you're allowed to boot your kernel. So that's one element. So you're not willing to boot a kernel that is not signed correctly. And also you have to sign U-boot with the specific tools provided by the vendor to make sure that your board is going to accept to boot your U-boot. Okay, because you have a two-step boot. First you boot U-boot, and then U-boot is booting the kernel. Okay, so that's for like a quick vision on how it works. So now what I propose is we can go on a real example. So may I share? I'm going to share a tab. Okay. Okay. So dashboard. So this is a factory. So this is our interface to Koji. Okay. So this is a community version. So you only need a GitHub account to connect onto it. If I connect, okay, you see that you just need a GitHub account to connect and you're in. And I'm going to look for my different projects. So this is a pretty empty one because I made it for this talk. So the first thing we see is the template. So this is what I told you about before. So that's typically something you import in your environment to have an empty template that you start to fulfill. And from this template, you build your own project. So if I look for my project, I can see here the different elements that we've seen in the slide before. So I have my firmware, my trusted firmware. I have my U-boot, my kernel, and the repository where is the different URL, and potentially also we may have here some initial certificate to enable the board to download stuff from your repository. Let's have a quick check on what we have here. So in this part, we see we have very little things. I'm going to make that bigger. We see that more or less this is coming directly from NXP, and we only have very limited amount of specific command to build that. This example is relatively simple because in this case, U-boot is not signed and there is no test to verify that you're allowed to load the firmware. Obviously, if the firmware had to be signed by some specific vendor tools, it would be a little more complex. Okay. If we look for the other application, we talked about U-boot. If we look for the different thing we have in U-boot, so in U-boot, typically, obviously, we have the spec file. We have a U-boot configuration, some extra flag. We talked about some binary blobs that need to be included because this board is an NXP solid run board, and we have some specific firmware. We also have a patch to support SMAC, okay, because in this example, we are not running SE Linux, but we're running SMAC. So if we were running SE Linux, we would have a patch for SE Linux, and we have a correction for some bugs they had, okay? So typically, this is what we have. And this is the spec file that we use, okay? And this spec file, when we execute it, is going to produce us some RPMs that we see here, okay? And this RPM is something you install, obviously, on your board, okay? Let's look for the last one that is important to us, the kernel. In the kernel, we have different files. Obviously, the most important one is the source code of the kernel that is obviously extracted from Git directly. Potentially, most of the time, you also have some patch that you have to apply. And then you have obviously the configuration for your kernel, which is typically, the config XMLs that we have in menu config on Linux, so nothing rocket science there. We see that we have nevertheless a few files, so it's a relatively big component. But as I said, this component is very generic, outside obviously of your specific configuration and what you want to include or not include in your kernel. But it's not too hard to maintain that. When you have done your BSP project, then you have to make something you can boot, and for that you're going to do an image. And so the image is slightly different because the image, in fact, is started from a kickstart. So it's not a spec file, but it's a kickstart. It is also the Red Hat tooling that we are using for that. And so if I look in my image and I check for the advanced setting, I see that my spec file is here. Okay, so that's my initial kickstart example. And here again, I would say it's a relatively complex, because depending on the board, the initial image you have to boot, you always have to do some fine tuning on where's your partition, how you want to share your disk, and a lot of different things like that. But there is very little maintenance on that. Okay, when it is in place, it does not move. Okay, and at the end of the day, obviously you may have some specific projects. So here we only have a demo on Modbus, and typically what you're going to do is this application is either going to be included within your image with your BSP, in which case when you build your BSP, your image, you take the kernel, the BSP, and your application, or you're going to build this application as a container, and you're going to have more kind of immutable operating system, and you're going to upload your application as a container. Okay, so this is when you create a project, you see you can create either a standard project like we have for the BSP, you can create an image project, as we've seen in the example where we want to have something bootable, and you can obviously import project, but we could also create a container project. One thing I forgot to show you is this. In the image, if I go here and I look for the build, okay, and I look that, I see that here we have effectively the final image, which is what you're going to boot on your board. So bmap is a special format that allow you to remove the zero from your distribution, so it makes the upload faster. Okay. From a timing point of view, that's something we did not check, but that also has some interest. If I look here for that, and I look for my kernel, and I look for the build, we see that the build of the kernel took 20 to 22 minutes, so it's a pretty long operation. And this is on the community stack. Obviously, if you build it on a commercial stack, it might go faster depending on, how powerful is your machine. But nevertheless, you're not willing to rebuild that every half an hour. Okay, it takes a lot of time, and but as I said, we normally don't change it much, except obviously when we have a new fix that are coming from the mainline, or eventually from the vendors. But most of the time, they're coming from the vendors. Okay, so that was for the demo. Let's finish very quickly with the slide deck that I had was here. So we were here. So what is important, in fact, is not only how you build your initial kernel, but also how you're going to maintain that for 10 or 15 years. Knowing that whatever you do and how generic you're willing to be, you still have some key components that are going to remain specific because of the customer configuration, because of the specific hardware, because of some security constraints, blah, blah, blah. So there are thousands of reasons why you have some specific things. So what you're willing to do is really to have a clear separation in between what is mainline, what is specific, and you want to use Koji and all the different tools that are available to maintain automatically your BSP. When your BSP is in place, then you want to use the Kickstart model or something else, but we use Kickstart for that, to assemble your BSP with the version of operating system you want run. and potentially with some middleware as well. If you have an immutable operating system, you probably have some, container engine, for example, that you want to be at that level. And also most of the time we have some application. At minimum, we have some security and supervision application, but even very often we have also some other application. And from that, you're going to generate an image, and you want to have the capability to update the image. And so this is the beauty of RPM, and that's a very strong point compared with Yocto, because it's very easy to build RPM and to keep up to date your image. Okay, so as a conclusion, Yocto, you have one or more layers. You have one or more providers. You can modify everything at any time from anywhere, and there is no long-term support. Okay, and we could add other things like it's also very long to rebuild stuff. Okay, because it often rebuild everything. If you move to the RPM world, you have one project per BSP, so it's a much cleaner approach. You have it's a standard user project, so there is no difference in between a BSP project, an application project, a container project, an image project. All of that is handled on the same way. All the modification are handled through Git, so you can keep your modification under control. Obviously, you have a team and user management, so you can decide who is allowed to read, to write, to test, to upload, to release, and so on. And you have a long-term support with automatic update. I don't say everything is automatic, okay? Otherwise, we would be more richer than we are. But you can optimize clearly the modification and the update. Okay, this is where we are working. So we are by the sea. If ever you want to sail, don't hesitate. Okay, we have a boat, so it's always a pleasure to receive people. And I just had a few links. As I said, the community versions that I use for my demonstration is publicly available, so you can play with it. You can run your application. You can. By default, on the community version, I think we support today 6 boards. So we have Renesas, NXP, Solid Run, Raspberry, obviously, Intel, and we also have a lot of other boards, but they are much harder to buy because they are specific to some customers. So we did not add them into the community edition. But if you have some specific board you're interested in, let us know. We're going to add TI pretty soon as well, because we've done the port for the Citara board as well. Okay, so that's it for me. If you have questions, I'm more than happy to respond to your question.
I have 2 questions.
Go
A
ahead.
very cool presentation. Are you running your own Koji instance servers and so on?
Yeah. Yeah, not only we run, so we have multiple instances of Koji. We have one that is for the community that we are running. We have one that is for commercial customers that use a share instance. And we also have some private instance for some customers that either run in our infrastructure or directly on premises with the customer. I would say most of the customer are big customer. You've seen the name, okay? Valeo, Stellantis, Renault, Thales, Total. And those people are not ready to share a lot of things, okay?
Right.
Maybe in the future, but not today. So for that reason, most of them want to have a private instance. So typically what happens is during the proof of concept phase, when they do the evaluation, they often run in-house. So we run their stack in our premises, and when they want to go to production, they want to transfer everything in-house. Yeah. I would say that's a typical model. Yeah. I'm not sure it's going to last for a long time. Okay, we see some more and more people wanted to run stuff on the cloud, but it's still pretty complex. Yeah.
My other question would be that do you manually create your spec files, or do you have some kind of auto-generating tooling from Yocto recipes to spec files?
I would say it's a kind of in between. Okay. In fact, we have 2 models when we want to integrate a BSP. First, if we're willing to implement a quick hack, going really fast. Or for example, we have a bug in RPM and we want to reproduce a bug in Yocto because the board is still under guarantee, and so we want to send the bug to the vendor. Okay. In this case, what we do is we use Yocto to produce. We kill big bait at the RPM and we rewrite the metadata of the Yocto RPM to fake Koji, and so Koji thinks that it produces the RPM when in fact it's not true. Okay, so that's a kind of quick add when we are willing to compare binary version produced by Yocto running on your stack, is mostly for quick test or for bug report. Okay, we have a second element where we stop bit bake at the early phase of the build, so just before it built, and we retrieve the different parameter and options that they would use for building, and we reincorporate that in the spec file. But to be honest with you, all those tools that we wrote at the early day of the project, now that we have this templating mechanism, are not that useful, because you know, you look inside Yocto layer and you just take the different parameters and options and you just translate them in your template, and most of the time it is faster. Okay, as I say, because Yocto write everything everywhere, okay, and you know, anyone in a BBE happen can change the configuration of the kernel. Okay, it's not like you have the configuration at the one single place. So the only way to really know what Yocto is going to do is by starting bit bake and looking for the final result. Okay, so I would say it's a kind of semi-manual process or semi-automatic, depending on, you know, whether you want to look positive or negative. Yeah. One thing I forgot to tell you about Koji, we also modify Koji because we do a cross build. Okay. And so we did not have to modify the core of Koji because Koji has plugin. So we implemented plugins. We had many exchange with Red Hat people on that sub when we did that. And in fact, as today, none of our customers are willing to buy ARM server, okay, because the IT is not ready for that. And so best case, what we can get when we run into a big customer infrastructure is they give us some VMware instance. And so we have to run with whatever they have. The second reason is something I did not talk about, but when you develop application, people are willing to develop not on the factory because that's a pretty long process. They want to develop from their laptop. And typically the laptop are Intel machines. So you also need to have a cross build for your Intel laptop system. Yeah. So for that reason, we also had to change Koji. Yeah. Yeah.
Are those plugins the Koji Builder ones?
I will be honest with you, it's not me who wrote those plugins. So yeah, I suppose this is where they are.
Yep.
But yeah, it's not me who wrote them. And as we wrote a kind of a gateway or front end on top of all your Red Hat tools. Okay, we have a single API to access all your services, so we don't really see directly Koji. And one of the motivation for that is Koji does not handle well the fact that you have multiple users with different access rights on who can do what. So we had to implement the access control layer on top of Koji and before Koji. There is also a second of kind historical reason is that in the past we were using OBS because we also did Tizen. You know, Tizen operating system was built by my team, and it's based on OBS. And so when we shifted to Koji, I told my guy, maybe in the future we'll have to change again. So I don't want to be dependent on any vendor API. So for that reason, I would say we don't really see, except few guys that are working at a very low level. Most of the people don't really see Koji. Yeah. Yeah. Even if I would be honest with you, sometimes we have bug where we have to dig down into the Koji log. Okay, but normally we should never. Okay.
Got it. Cool. Thanks.
So we're a little over time, but if anybody has any further questions, let me know. We can also take some of this discussion to the chat room on Matrix. Okay. Yes. Thank you very much, Philip. It has been a really, really interesting discussion. to see how all this comes together.
Okay, thank you for your time.
Quite an operation.
Yeah, you just try it, and if you have issue, we have support on Matrix or on the CentOS mailing list. I will be more than happy to respond. Yeah.
Fabulous. All right. Well, thank you again. Thank you very much, and thanks to you all for coming. We will talk to you soon.
Bye bye.
Thank you. Bye.